Okay, the next property that we looked at is vapor pressure. This is again, it's just revisions because you have learned about this in your thermodynamics, even in your physics. So what is vapor pressure? So by definition, it is the pressure at which a liquid boil or change phase from liquid to gas. It is actually a function of temperature and increasing with temperature. So meaning that at higher temperature, the equivalent vapor pressure is actually higher. So conversely, the boiling temperature actually decreases when the pressure decreases. So looking at that, boiling can actually occur even at low temperature if the pressure is actually low enough. And this actually gives rise to a serious problem in fluid machinery, which is called cavitations, and which actually cause a lot of damages to fluid machinery. If you look at the variations of vapor pressure against temperature, so we can see that, well, at pressure of 1 bar, the boiling temperature is 100. But if we reduce the pressure, the boiling can actually occur even at 20 degrees C. If the pressure is equal to about 5 kilopascal, the boiling can actually occur at 20 degrees C. When boiling occurs, change of phase will happen. If anywhere within the fluid machinery the pressure is low and it actually reached the value of vapor pressure, then it will start to boil and change phase from liquid to gas phase. So if you consider flow in nozzle, so let's say I have a nozzle. So in nozzle, the pressure is lowest at the throat. So if I plot the pressure, it will look like this. If this pressure here is actually below vapor pressure, what will happen is that change of phase will occur here. So it means that the liquid here, when it reaches this point here, will change into gases. So bubble will be formed. But when it moves to this region here, where pressure is higher, it will change phase again from gas phase into liquid phase again. And when that happens, there'll be release of latent energy, and which actually cause damages to fluid machinery. This figure here shows some examples of what happened when cavitation occurs. In turbo machinery, for example, in the regions where pressure is lower than the vapor pressure, cavitation will occur and it will cause damages to the plates. And here is examples of damage due to cavitation in hydro plant draft tube. So you can see here, this is a draft tube which is quite big, and this is a figure of a human. So this is the kind of damages which has occurred due to formations of cavitations. The last fluid property that we looked at is speed of sound. Speed of sound is defined as the rate of propagation of sound wave in the fluid. And normally we use the symbol A to signify the speed of sound. The formula for speed of sound is root gamma RT. For example, for air at 20 degrees C, the speed of sound is 343 meters per second. If you consider an object which is stationary and emitting sound wave, if we can draw how the sound wave propagate within the fluids, so it is actually the sound wave will move equally in all directions at a speed of a, right? But if the object here is also moving, so let's say it's moving to the right with a finite speed, what will happen is that it will look like this. If the speed is actually exactly equal to the speed of sound, then it will look like this. And finally, if you consider the case whereby If the object is moving at a speed which is higher than the speed of sound, it will look like this. The ratio of velocity divided by speed of sound, which is v divided by a, is actually called Mach number. So in this case, this is Mach number is equal to 0 since velocity is 0. So in this case, this is Mach number is equal to 1. And in this case, Mach number is bigger than 1 since the velocity is actually bigger than the speed of sound. And this one here is Mach number is less than 1. So there is a name for this. This is called subsonic. This is called sonic. And this is called supersonic. And generally, if the Mach number is less than 0.3, the fluid can be considered to be incompressible. Whereas if Mach number is bigger than 0.3, you cannot assume the fluid to be incompressible. The compressibility effect has to be taken into account. In the case of supersonic flow, you can see that the object is actually moving at a speed which is higher than the speed of sound, right? So if you have ever observed, for example, a supersonic plane, supersonic fighter jet flying past you, you would have noticed that you cannot hear any noise when the aircraft actually pass you. You can only hear the noise only when the aircraft has passed you by a certain distance. You can only hear the sound when the sonic boom actually pass you here. So in this case, when the aircraft actually already reached there, only then this portion here hit you, and only then you can hear the noise. So that's bring us to the end of this chapter. So if I can recall, so we have started the chapter by looking at definitions of property. And then after that, we have looked at properties involving mass and weight, followed by properties involving flows of heat. Then after that, we have looked at shear stress in moving fluid, which is actually very important because shear stress is the one that actually causes the resistance to fluid motions. Then we have looked at surface tensions, vapor pressure, and speed of sound. Having learned about the fluid properties in this chapter, next chapter we will look at fluid static.